Hello everyone, my name is Antoine Saporta and I'm a PhD student at Valeo.ai and Sorbonne University in Paris. I am pleased to present you our work on multi-target adversarial frameworks for domain adaptation in semantic segmentation. Semantic segmentation is a computer vision task that associates a class label to each pixel of an input image. Segmentation models have notable real-world applications, such as autonomous driving systems. However, training those perception models in a supervised setting requires a lot of annotated data, which is extremely expensive to acquire manually. Supervised domain adaptation brings some solutions to reduce the labeling efforts required for training perception models. Its goal is to leverage data from a fully annotated source domain, for instance synthetic, to train a model on a non-labeled target domain. Practically, UDA methods aim at bridging the domain gap between source and target data. However, most previous approaches are restricted to single-source, single-target settings. When single-target UDA approaches do well on one target, they fail to generalize to more target domains. In this work, we tackle single-source, multi-target, unsupervised domain adaptation, whose goal is to learn a single perception model that performs on the multiple target domains. More specifically, we propose frameworks, the multi-discriminator and multi-target knowledge transfer, which are dedicated to this new task of multi-target UDA for semantic segmentation. To evaluate our models, we also propose multiple evaluation benchmarks based on existing semantic segmentation datasets. The first proposed framework is the multi-discriminator architecture that extends single-source, single-target adversarial methods. It is built on a traditional semantic segmentation model with additional discriminator networks whose goal is to align the distributions between the multiple domains. In this framework, we introduce two kinds of adversarial alignment. First, a source-target alignment for each target domain, which is similar to what is usually done in single-target adversarial training. And secondly, an alignment between each target and the other targets to further close the gap between the multiple target domains. The second proposed framework is called multi-target knowledge transfer. This model adopts a multiple teachers single student approach in which the segmentation network is split into multiple branches. Each target-specific branch is trained to handle a single target domain by bridging the gap with the source domain. Simultaneously, these target-specific branches serve as teachers for a target-agnostic branch that fuses their knowledge in order to perform on all the target domains. In practice, target-specific classifiers are trained similarly to single-target UDA adversarial methods. Each of these branches aligns its target domain to the source domain with a discriminator network while optimizing a segmentation loss on the source data. Meanwhile, the knowledge of these target-specific branches is transferred to the target-agnostic classifier by minimizing callback-level divergences between their predictions. We test our frameworks on multiple UDA settings based on Urbatsin semantic segmentation datasets. We compare the performance of our framework to those of single-target baselines as well as a multi-target baseline which considers the combination of the target datasets as a single target domain and is trained accordingly. In this three target domain setting, we see that both our frameworks outperform every baseline on the mean intersection over union average metric, which measures the multi-target performance of each model. Moreover, MTKT actually improves the performance on each individual target dataset compared to their respective dedicated baseline, which is not the case for the multi-target baseline. We further illustrate the benefit of our work on a direct transfer setting in which the models try to generalize to a previously unseen target domain at test time. In every setup, MTKT shows better performance compared to the multi-target baseline, highlighting how the features extracted by this framework are more invariant to the domain. Finally, we display a couple of test examples on GTA5 to Cityscapes plus IDD setting. We can see that a multi-target approach heavily reduces classification artifacts on the produced segmentation maps, as shown on the road for the Cityscapes example. Moreover, we can also note that MTKT better detects some smaller objects compared to the dedicated single-target model, as can be seen on the IDD example. Thank you very much for your attention. Feel free to join us during the poster session should you have any questions.